So, welcome friends. In the last lecture, we have developed all the necessary tools which is required for running the sixth of aircraft equations of motion. So, without wasting any further time, let us quickly switch back to MATLAB. So, I have written the code already here. First, let us run the sixth of simulation directly in MATLAB. So, here the initial condition will remain same, that is 30 into cos t v cos alpha. So, here alpha is assumed to be initial angle as 2.1471 degrees, and side velocity I am considering it as 0, and the downward vertical component velocity is we calculated again, it was v sine alpha. Here total v is 30 meters per second, sine into alpha, and the rates I am assuming initial conditions to be 0. Similarly, the lateral parameters phi naught I am considering it as 0, that is roll angle, initial roll angle, and initial yaw angle, and theta naught remains same, that is the alpha equals to initial alpha naught equals to 2.1471 degrees, and initial position x naught, y naught, and z naught also I am considering the initial values as 0. Now I am putting these initial conditions in a vector in this format like we did for 3 DOF simulation. So, initial conditions we have u naught, v naught, w naught, p naught, q naught, r naught, phi naught, theta naught, xi naught, x naught, y naught, and z naught. So, we have total 12 states. All right. Time span I am considering the same, 0 to 300 seconds, and the ODE solver I am using the same, that is ODE 45, which uses Runge-Kutta equation. The output is t and the states. Here states we have 12 instead of 6 that was there in the 3 DOF simulation, and the syntax for ODE 45 remains same, that is we call the function file equations of motion comma the time span, which is 0 to 300 seconds, with the given initial conditions that we have over here. And when it comes to line number 24, it looks for equations of motion, and I have included directly in this MATLAB file, that is dy dt equals to equations of motion, as again this is a tilde, you can also include it as time, and y is a vector of 12 states, and the output file I have named it as output variable, the name I have named it as dy dt, and these are the parameters that remain same. So, I have not written the lateral parameters. Let me write the lateral parameters first, so that it will be easy for you to simulate by yourself. So, here we have Cy naught equals to Cl naught equals to Cn naught equals to 0, Cy beta equals to minus 0.98, Cl beta equals to minus 0.12, Cn beta equals to 0.25, Cyp equals to 0, Clp equals to minus 0.26, Cnp equals to 0.022, Cyr equals to 0, Clr equals to 0.14, Cnr equals to minus 0.35, Cy del A equals to 0, Cl del A equals to 0.08, Cn del A equals to 0.06, Cy del R equals to minus 0.17, Cl del R equals to 0.105, Cn del R equals to minus 0.032. Again, these parameters belong to the Aerosonde UAV. Which I have considered from a book. by Randall Beard, Small Unmanned Aircraft. And these derivatives, they belong to a particular equilibrium point, particular trim value. Please note that to get these derivatives, it is actually not easy. Lot of effort is put to find these values, and there are multiple ways to get these values. Of course, one is the wind tunnel test. Multiple wind tunnel testing is done to get the approximate of these derivatives. Second way you can find is through CFD simulation. Third method is the linearization technique or small perturbation theory. Which we have already covered in the first part of this course. Another method to obtain this derivative is flight testing. So after flight testing, we can use system identification techniques. We can use system identification techniques to find these derivatives. So the point I want to stress here is it is not easy to get these derivatives. All right. Now let us go back to MATLAB. Here mass Ix, Iy, Iz, these are the inertial parameters. Then product of inertia, gravity I am considering 9.81, sea level density 1.225, span, again the thrust remains same, 2 kgs of thrust multiplied by 9.81 to get in newtons. We know the thrust should be in newtons, and these are the aerodynamic coefficients which I have already mentioned before. In case I missed any coefficient, you can note it from here. And these are the inertia expressions, gamma, gamma 1, gamma 2, gamma 3, and so forth. Now finally I am letting MATLAB know that these are the states at u, v, w, velocities in the body frame. Then we have angular rates p, q, and r. Since there are 12 states, I am letting MATLAB know that these are the states. Phi is the 7th state, theta, xi, similarly x, y, and z. So this is basically unused in the equations, but that's all right. So we in 3DOF we had v equals to square root of u square plus w square only, but in 6DOF we'll be having v equals to square root of u square plus v square plus w square, that is total velocity magnitude. And we only added alpha equals to tan inverse of w upon u. Here we have beta also, a sine small v upon capital V. All right. Then we have aerodynamic forces and moments. I have modeled here CL as CL naught plus CL alpha into alpha plus CL del E into del E, CD as CD naught plus CD alpha into alpha. You can model it as CD equals to CD naught plus KCL square also if those parameters are given. And the side force coefficient Cy naught plus Cy beta into beta plus Cyp into Pb by 2V, that is we are non-dimensionalizing the parameters, Cyr into Rb by 2V. Then we have Cy del A, Cy del A into del A, that is aileron deflection, then Cy del R into del R. Then the rolling, pitching and yawing moment coefficients are given in this format that we have already discussed. For example, Cl is Cl naught plus Cl beta into beta plus Clp into Pb by 2V plus Clr into Rb by 2V plus Cl del A into del A plus Cl del R into del R. Similarly, Cm, Cm naught plus Cm alpha into alpha, Cmq into Qc by 2V, Cm del E into del E. Then finally, finding the lift, drag and the side force, half rho V square S into Cl. So Cl we have already found it here. Similarly, CD we found in this 75th line code. Cy we have found is 76th line code. All right. Next we have moments. Moments about x-axis, moment about y-axis, moment about z-axis, half rho v square s into b into cl. Cl we have found it here. Similarly Cm and Cn. The throttle is given as Tmax into del T. Del T we have assumed it as 0.5, that is 50% of throttle is always applied during the entire simulation run. Then we have Fx, forces in x direction, minus d cos alpha plus L sin alpha plus T. This is Fz minus L cos alpha minus d into sin alpha, and side force is simply side force coefficient, that is not coefficient, forces in y direction, this is the side force. Hence we had derived this equation earlier. And we can write even in the terms of accelerations in x direction, y direction, z direction. The process remains same as of 3 degree of freedom equations of motion. So Fx by m minus g into sine theta, that is linear acceleration along x axis. Similarly acceleration about y axis, and AZD linear acceleration along z axis. So du is AXE plus r into v minus q into w, similar to the 3 of equations of motion. And finally, so this is u dot, v dot and w dot. Then we have accelerations p dot, q dot and r dot that we have derived in today's or in the last week's lecture. Then we have phi dot, theta dot and xi dot expressions, kinematic equations, and finally the position derivatives x dot, y dot and z dot. And the output vector is dy dt, that I have included it here, dy dt. So I am not taking any other output here, I am interested only in the 12 states. Hence here u dot, v dot, w dot, p dot, q dot, r dot, phi dot, theta dot, xi dot, x dot, y dot and z dot. Now after this, when the MATLAB code reaches to 127th code, after it comes out of the function file, we need to MATLAB know that the first column belongs to u, second column belongs to v, and so on and so forth. So we have 12 states. So if I run this till here, let me run this. So we have states. So we have 12 states over here. If I double click over here, we get these 12 states, and we are letting MATLAB know that which column is what. All right. I am removing this break line code. Next we have to calculate again v, alpha and beta. So square root of u square plus v square plus w square. Since u is a vector now, we have to do element to element multiplication. Hence I put here dot, otherwise it will be throwing an error. Similarly alpha a tan inverse w by u and a sin v upon capital V. Now finally we are ready for plotting the results. So in the figure 1 I have included plotted subplots t with u, and then second plot is with velocity, side velocity small, and then third is the downward component of velocity w. So the figure 1 indicates velocity components in body axis. Figure 2 indicates the rates, angular rates, where we have p converted it into degrees, that is radians to degrees multiplied by 180 by pi. Then the second plot is pitch rate q, and the third plot is r. And figure 3 indicates plots Euler angles, that is phi, theta and xi. This also I have converted into degrees. And finally in figure 4 I am plotting v total velocity separately, that we have calculated it here in line number 133. Similarly I plotted alpha and beta here. And in figure 5 I am only interested to know altitude, and I put here minus sign here. Since z direction is pointing towards the center of the earth, we would like to know whether the altitude is increasing or decreasing with respect to the body axis, hence I put here minus sign. So now let me continue running this code and let us look at the plots. So we look at the plots one by one. First is U, V and W. So we know that we have already applied the trim condition, that is delta E trim and alpha trim. So here the velocities, forward velocity is stabilized to around approximately 30 meters per second. And since there is no perturbation or anything towards the body y axis, this remains 0. And we have small w over here, which is approximately 1.1 meters per second. Now going to plot number 2. So there is no deviation in the lateral plots. So there will be no deviation here. So we get again the pitch rate approximately equals to 0. And in figure 3 again, there will be no deviation in phi and xi. There will be deviation or oscillation in theta, which is stabilizing to approximately 1 degrees. And figure 4, I have directly plotted the total velocity. Here we have total velocity again approximately 30 meters per second. Alpha is up to 2.14 degrees and beta is 0. And here again we observe that the altitude is actually decreasing. So since there are no variables in lateral, so it is behaving as if it is 3 degrees of freedom motion. All right. Now let me just introduce a disturbance in the lateral variable. So it is mostly affected by the angular rates. Let me put it as 0.1, which is radians per second. Now if I run this code, let us see the plots. Now we have a small deviation in the side velocity v. Let us go and check, yeah, p and r. So since I have given the deviation in p, and we know that lateral and directional dynamics are always coupled with each other. If there is a deviation in p, then there will be deviation in r as well, that we can observe over here, although it is coming to 0. Since the alpha trim we have applied and delta E trim we have applied, and phi reaches to approximately 0.4 degrees and then goes back to 0 for the wings level condition. And xi, actually we don't care in which direction the aircraft is heading. Theta, actually it is important. Theta is approximately around 1 degrees. Here we have now again velocity is approximately 30 meters per second. Alpha is again approximately 2.14 degrees, and beta also it goes to 0. Now likewise I said earlier that alpha and w have 1-to-1 relation. So likewise beta and small v have 1-to-1 relation. If there is small v, then there will also be beta. Let me open the v plot. So if there is a small v component, then there always be beta component. If there is beta, then there will be a small v component. So there is always a 1-to-1 relation between these two. And finally, going to figure 5. So here again we observe that the altitude is decreasing by 200 meters. Now let us go a step further. Let me bring this back to 0. And we know that for longitudinal stability, Cm alpha should be always less than 0. So here we have Cm alpha, here it is negative. For longitudinal stability, we have Cm alpha should be negative. So let us see what happens when Cm alpha is not less than 0. Now I will try to run this simulation. So although the simulation has run, so let us see the plots, phi, theta and xi. So here theta is going up to 5 into 10 to the power 4, which is unrealistic. So that means it is continuously doing a somersault, which is definitely not acceptable. So as soon as I put Cm alpha back to negative, then we have proper results. Theta is back to its normal 1 degrees. All right. So let me write a note over here. So for longitudinal static stability, Cm alpha should be less than 0. So for positive attack angle, pitching moment must decrease to bring nose down and restore equilibrium. So when we have Cm alpha less than 0, the aircraft resist deviations from its trimmed angle of attack maintaining stability in pitch. So here Cm alpha, we generally call it as longitudinal static stability derivative. Static stability derivative. All right. Now let us look at another variable. So here we have Cm alpha negative. All right. Now let us look at CLP. Here CLP was negative. Let me keep it as positive. Now run the simulation. So here still we have good results. Why? Because we haven't introduced any deviation in the lateral variable. So let me put again P here, P naught as 0.1, and I am running the simulation. It is running, still running. If you see the bottom left, it is showing as busy. It is still running. So what it means is the solution is not able to converge to a finite value. So ultimately there is no solution for this. That means the aircraft is no longer in equilibrium point. I am stopping this simulation and then I check it with CLP, change it to minus. Let me put it as minus over here and run the simulation with the disturbance in the lateral directional coefficients. So here we still observe the aircraft returns to its equilibrium position in finite time. All right, so that's the significance of CLP. Now what is CLP? Let me write it down. So CLP is nothing but roll damping derivative. All right. So for positive P, for positive roll rate, so what do you mean by positive roll rate? That is right wing going down when viewed from behind. All right. So right wing is going down, that indicates positive P. So we need to generate negative rolling moment. That means left wing should go down. So negative rolling moment must be generated. That is CLP less than 0. So what we did in simulation was we kept CLP as positive. So that means once the right wing went down, so if this is positive, it further went down. So it should have initial tendency to come back to its original position. So the hence CLP should be negative. Then finally, let's go back to another variable, that is CNR. This is also negative. Let me keep it as positive over here, and we have initial disturbance in the roll rate. I am running the simulation now. It is running, showing busy here. So again we are not able to get a converged solution. All right. So I am stopping it here. You can try it of your own. So let me put it to back to minus. Now what is CNR? CNR is yaw damping derivative. All right. So for positive yaw rate, that is for positive R. So what do you mean by positive R? Right wing going backwards when viewed from behind. So when we have positive yaw rate R, so then negative yawing movement must be generated. That is, now left wing should go back in order to be stable. So that is negative yawing movement must be generated. That is CNR should be less than 0. And when we tried CNR greater than 0, so with the initial disturbance, the right wing was already behind. So then what happened? It kept on going backwards. That means it kept on yawing. But for stability, we need it to go back to its equilibrium position. So hence CNR should be negative. All right. Now let us write a note here. So negative CM alpha, CLP and CNR are the part of system natural dynamics and restoring forces. Ensuring the eigenvalues of the system dynamics have negative real parts, which is the requirement for for stability. All right. The Cm alpha significantly influences the short period and Fugard mode. If you are not sure what is short period and Fugard mode, please refer the first series of this course. CLP and CNR impacts the roll subsidence. That is one. It also impacts Dutch roll and spiral mode. All right. So similarly, we have CL beta, it should be less than 0. This is for roll static stability derivative. And we have Cn beta greater than 0. This is for yaw static stability derivative. I am not going to test this now. I am leaving that as an exercise to you. Next, we have Cm delta E, Cl del A, and Cn del R. So we call this as primary control derivatives. Followed by Cl del R and Cn del A. These are usually pretty small values. So these are cross control derivatives. So control derivatives that is both primary and cross control. So control derivatives can be thought of as gains the larger the value of control derivative, the larger the magnitude of movement produced for a given deflection of control surface. Now let me go back to MATLAB again. So I want you to, as an exercise, change these parameters to plus to negative and vice versa, and see how the model is behaving. And also we have Cm naught as negative. So we know that for trim, for it should be Cm naught should be positive, so that we can trim the aircraft at positive angles of attack. But we have Cm naught here as negative. That's all right, because we have already taken the alpha trim condition. We have elevator in the negative direction. That means it is continuously pitching up. It is trimming the aircraft at positive angle of attack. All right. So I want you to change these parameters and see how the aircraft is behaving one by one. So that I leave that as an exercise to you. So now we are done the simulation of MATLAB, simulation of aircraft equations of motion in MATLAB. Now let us include Simulink as well. So this is the Simulink model that I am trying to call from here, sim six-stop underscore simi dot slx. So initial conditions remain same, u naught, v naught, w naught, and so forth. This is the initial vector, and this is the SLX model. Let me go to the Simulink model first. All right. So let me just delete it. Okay. So I'm not going to build this model again from scratch. So you can look at it. I'll open this MATLAB function file. All right. So here is the MATLAB function file. Here everything remains same as was in the MATLAB.m file. Here output is of course the 12 state vector. I've also included movement about y axis, similarly coefficient of moment Cm about y axis, and this is the function file equations of motion, and everything remains same over here, and this is the output vector u dot, v dot, w dot, and so forth. So this is the function file. So this I am actually integrating over here with the initial conditions as y naught. All right. If I go to the modeling, model settings, I have used as a fixed step over here 0.01 OD4. You can also use a variable step, it's up to you. Stop time is TF that I have mentioned in the MATLAB code. And here I am extracting all the variables u, v, w, p, q, r, phi, theta, xi, x, y, and z. This symbol indicates the terminator. It means we are not plotting this. We are interested in these parameters. In z, I have multiplied this by -1 so that we know that whether the altitude is increasing or decreasing. And also I have transformed these variables to workspace model. This is the workspace to workspace as we did in the 3DOF simulation model. And I have extracted v, alpha, and beta. What I have done here is I have added one more MATLAB function over here, and in that MATLAB function the only inputs were required was u, v, and w, and I calculated v, alpha, and beta separately. So it is up to you, you can extract directly from this model as well by writing here it as v, alpha, and beta. So here the output we get here v, total velocity, attack angle, and the side slip angle. All right. And here I have converted into radians to degrees, and this is to workspace as I said before. Now let me run this code directly. Let me save it first. All right. Now after this the MATLAB reaches to the 11th line. It runs this Simulink model, and then I am extracting that data v, alpha, and beta from there, the out to workspace file that I created, sim y, and then I am plotting here. Figure 1 I plotted with v, alpha, and beta. V, alpha, and beta. So here alpha I have already converted to degrees, beta I have already converted to degrees, hence I have not written here alpha into 180 by pi. So this is in the subplot we have t comma v, then alpha and beta. All right. So now we are ready to run this code. Let us see, are we getting the similar results or not? Yes. So indeed we are getting the similar results. So total velocity is around 30 meters per second. Attack angle is approximately 2.14 degrees. Side slip is 0. So let us see the other plots. This is theta. Theta should be around 1 degrees. Yeah, it is around 1 degrees. since there is no perturbation in the lateral variables, this phi, r, these should all be around 0. Similarly, p should be 0. Yes, it is. And q should go towards 0 after certain time of interval. Yes, it is going to 0. This is the forward velocity, which should be around 30 meters per second. Side velocity should be 0 and small w should be around 1 or 2 meters per second. Yeah, it is around 1 meters per second. And this is the total movement about the y axis, which is going to 0 after certain time. And this is the coefficient of movement. And the altitude, it is actually decreasing. All right. And this is the total velocity v, which should be around 30 meters per second. Alpha should be around 2 degrees. Yes, it is 2 degrees. And beta should be around 0. All right. Now let me change the initial conditions again and put p naught as 0.1. You can put perturbations or deviation in other parameters as well. It is up to you. So let me rerun the code. So here we observe again perturbation in one lateral variable will instigate perturbation in another variable. That is, now here it is, the perturbation is in side slip angle beta. V is again still going towards 30 meters per second, and alpha is around 2.14 degrees. Let me go to the MATLAB and Simulink and rerun the code and rerun this scope, and we get the similar results. Theta is approximately 1 degrees. Yes, it is. Similarly, velocity, it is approximately 30 meters per second, and the altitude is actually again decreasing. What I also want you to do is change this delta E that we have given the trim angle of trim elevator deflection, change this to any arbitrary value and see now then what happens. So this, I leave this an exercise to you. Similarly, you can change this variable delta A, delta R and observe what is actually happening apart from changing these variables as well. All right. So now we have done simulation for aircraft 6 TOF both in MATLAB and in Simulink. All right. Now the last one is left is the Simulink 6 TOF block. So that we can get it from here, 6 TOF block. Now let me go back to the equations, 6 TOF equations that we have seen earlier. All right. So we see over here that m into Vb dot plus omega, omega is PQR cross total velocity V. So let me write P dot Q dot on R dot, or U dot, V dot and W dot. Let me write the omega dot first from this expression. Yeah, here it is, omega dot. Let me write omega dot. We have I inverse MP moments minus omega cross I omega. Similarly, we have velocities U dot, V dot, W dot in this format, 1 by m FB. So whatever equations that we had written before, we simplify these equations in that format, we get those equations. Now this is in matrix form. Equations are same, only the form is different. All right. And similarly, we had a theta dot equation as well. Let me write only this equation, that is theta dot equation. Theta dot can be written as q cos phi minus r sin phi. Minus r sin phi. All right. Now let us go back to the Simulink model and see here. Likewise, in 3DOF model, we have here the inputs as forces. Only this time this is in a vector form, Fx, Fy and Fz, and the moments are in Mx, My about x, y and z axis. So this I am leaving as an exercise to you. So all you have to do is put the forces vector here, similarly moments vector here, like we did for 3 equations of motion, and we have output here velocity phi theta xi, dcm the direction cosine matrix, velocity in body axis, rates pqr, and then accelerations, and in the acceleration in the body axis. Now when we double click this, what we get over here, the units is in metrics, mass is actually fixed, we are not changing the mass. It needs input as xe, ye and ze. Similarly, in initial velocity in body axis u0, 0, 0. Similarly, orientation angles phi, theta and xi, initial body rotations pqr, and initial mass. So one thing we also had, let me go back to the 3DOF model. So in the earlier lecture we have used this model. If you double click this, then we enter the parameters over here as well. The initial velocity is 100 meters per second. Initial body attitude, that is theta naught, we need to enter over here. This is body rotation rate, q naught, initial incidence, that is alpha naught, xz, initial mass 13.5 kg that we had used, and inertia also was given. So I think I missed to open this block in the previous lecture. Anyhow, so we need to enter the parameters. Similarly for 6TOF as well. So here we have again x, e, y, z, e, body components u, v and w, roll, pitch and yaw, p, q, r, initial mass, and inertia matrix will be here, not a scalar, but it will be a matrix form. All right. And we need to give as the input as fx, fy, fz, which is again a matrix. Similarly, mx, my and mz. Now let us look what is underneath this mask. So here the equations, we are expecting that here equations will be already be integrated in this model. Let me right click this model and check, look under the mask. So control U. All right, I will just enter control U. So this is what is underneath this mask. I just pressed the space button in the keyboard and we have the full view of the model over here. Now let us first focus on, to get confidence in this model, let us first focus on theta dot. Theta dot is q cos phi minus r sin phi. Let us check, do we have this equation in this block or not? Of course it will be there, we just need to look carefully. So if we see this block Euler angles, if we are integrating these Euler angles, we should get Euler angles. Control U, space button, yes. So if we see, if go back to the equation, what are the inputs required? The inputs required are the Euler angle itself, phi, theta and psi, and the rates, angular rates p, q and r. And this equation theta dot should be integrated. All right. So where we have an integration symbol over here as well, and the inputs are of course the angular rates p, q, r and the Euler angles here. So when we integrate this, we should get phi, theta and psi. Let us see, do we have that theta dot equation here or not? So theta dot is this equation. All right, the first input is p, q and r. So let me write over here. So there are actually 9 inputs, p, q and r, then phi, theta and psi, sine of phi, sine theta, sine psi, cos of phi, cos theta, cos psi. Let me write here. So we have 9 inputs, 1, 2, 3, 4, 5, 6, 7, 8 and 9. The first 3 input is p, q and r. Let me write over here p, q, r. Next input is sine of phi, sine of theta, sine of psi. All right. So I have sine of phi, sine of theta, sine of psi. All right. Next we have cos of phi, cos theta, cos psi. Cos phi, cos theta, cos psi. All right. Now let us see the theta dot expression. theta dot, it is saying the inputs are 2 into 7. Theta dot expression is, let me rewrite it here, q cos phi minus r sin phi. Q cos phi minus r sin phi. So it should be, the q variable is 2, input is 2, cos phi is here is 7, r is 3, and sin phi is 4. So you should have input of u of 2 into u of 7. So we have here u of 2 into u of 7 minus u3, u of 3 and u of 4. So this is how we check the equations. So similarly, you can check it for phi dot and xi dot. All right. So let us give a check on another equation that I have written over here. All right. So omega is nothing but p dot, q dot and r dot equals to I inverse mb minus omega cross I omega. So let us see where the block is actually calculating the rates. So here we have p dot, q dot and r dot. So here it is actually integrating to get p, q and r. All right. So let us see what is happening in this block. All right. So we have here I inverse equals to mb minus omega cross I omega. So first let us multiply I into omega. What do we have here? Yeah, so here we have I into omega, it is multiplying here I into omega, which is again the cross product of PQR cross I omega. Here we have cross product of PQR. Here A is what? Here A is PQR cross I omega. This is cross I omega, and this is having a negative sign over here. This is negative sign. So we have a negative sign over here. Perfect. Then the moments are added. Yes, we have moments are added, and we see here this another term, that is I dot. So since the mass is actually fixed, inertia is not varying, so this will be 0 in this case. And finally we have I inverse multiplied by this whole equation, inverse of this. So here this is I dot. So if you double click this is the product block, this is multiplied by this I inverse, this is I inverse. So finally we get p dot, q dot and r dot equation. Now let us check, finally we can check this as well, u dot, v dot and w dot. Yeah, so here we have velocity in body x axis. All right. So here it is actually integrating this. Okay. Let us check the expression, that is F upon m. So here we have, yes, we have here forces divided by mass. All right. F upon m minus omega cross Vb, that is PQR cross the velocities. Here we have, this is the cross product, but the cross product here is we have PQR cross Vb. Here it is A cross B. Here A is U, V and W. So that's why he has considered plus over here. See, it is C equals to A into B. So if we can write this as 1 by m Fp plus Vb cross omega. That is what is represented over here. All right. So finally we get velocities in body axis. Likewise, I encourage you to explore this model and plot the 6-TOF simulation by yourself. So more or less we are done with this 6-TOF simulation, and regarding the examination, there will be no MATLAB or Simulink environment which will be provided. The questions will be such that it can be easily solvable using a simple calculator or in pen and paper. If you have any queries or any questions, you are suggested to put it in a discussion forum. In fact, you are encouraged to put any query in the discussion forum. Course instructors and the TS will ensure to answer your query as quick as possible. And if you would like to reach me, you can contact me at this email ID, p R A B H I T K @gmail.com. So Prab IITK, Prab IIT Kanpur @gmail.com. So let us stop it here. Thank you.